Hi everyone, a lot of people know me. My name is Paulina. I'm applied scientist in Amazon, and today we will be talking about ensembles, ensembles in general, and with focus on NLP and LLMs to be more topical to our days. So why LLMs fail in practice? There are several reasons, but mostly they just prioritize sound and plausible to actually fact-checking what's happening. And another reason is we fine-tune them for some specific problems, and they become overconfident on that and fail every other thing. It's especially noticeable if we're talking about some complicated problems like summarizing several documents where it started creating, for example, citations that was never there and just use something else. And that usually makes LLM very unpredictable, and it's hard to use it in the downstream tasks. So a little bit more about the problems. So everybody knows hallucination. Basically, LLMs create the thing that wasn't there. It's usually website links, citations, and other stuff. Or it can just misplace confidence. For example, if we asking about something out of its general scope, it prefers to actually create some answer instead of saying, I don't know. Here's an example from me using ChatGPT. I'm asking it about something non-existent, and instead of saying, hey, this is not a thing, it's giving me very long, very well-written answer, to be fair. And this is another example. It's not hallucinating facts. This is existing hotel. Although in my request, I was asking about hotels near Prague, and this is near the border of the Czech Republic, which is not very helpful for me, as I can tell. Other problems with LLMs is biases. There is a lot of, usually when we have a lot of problems with the data, it can be toxic. We, for example, train it on Twitter, which is not very great for being nice to people. And as a result, we get the LLM, which is toxic to people or just gives misinformation. About toxicity, you probably remember the situation with the Grok, again on Twitter, around like 3 weeks ago. It was turned off for a couple of days. And for disinformation, for example, recent research asked the Claude model to output the suggestions for how much a woman who is a senior in medical field should ask when she applies for a new job. And it turned out it's 20% less than what it suggests to the mail requester, which is, for example, another problem with LLM. And the next problem is catastrophic forgetting. So let's say we have one model, and we actually need to kind of train it to understand new data. We give it news, we give it new, I don't know, shows, books, etc. And we continuously update the weights. It can have negative effect because it leads to loss of the general knowledge, and it leads to model being things that switching between different tasks is very complicated. This is the example of the GPT-4 accuracy from March to June, and it actually went down just from the continuous updating, and it just forgot what it was trained for before. Apart from that, there is obviously issues with how expensive it is to train LLM, how it's hard to get an output, and we usually face like high costs and high latency when we work with this. Another thing is error propagation. So basically, if we feed the LLM the bad data, or we have some issues with the training process or fine-tuning process, it usually, the whole LLM fails. And single model usually has no way to check if it's doing something wrong. Another big problem is uncertainties for LLMs. Basically, uncertainty is a big problem for all the neural network, and I'm pretty sure for other machine learning models as well. But it's also very noticeable in LLMs. What is the reason? Usually we fine-tune LLM for something specific, and if we have maybe, it's usually the case, we have a very limited number of data for the specific problem, and as a result, final LLM overfit on this data and super confident on something from the training data and has super incorrect answers for everything else. This is the big issue for the risk-sensitive area, like if we're doing something related to medicine or legal actions, or even if we do like some content moderation for the social media. Another big problem, it is very, very expensive, as I already mentioned. So we can see if we're talking about like original transformer or BERT, maybe a regular person or small startup can actually afford that. But if we're talking about modern LLMs, we kind of done. Like the costs of training one single LLM is actually not achievable for a regular person, and it's even harder if we want to fine-tune it for like multiple tasks, or if we do continual learning, so we want the model to stay up to date with everything. It increases the cost like n times because we need to do it constantly. Again, so basically what is happening here is the single point of failure and lack of diversity. We have an error in data, it will be propagated to the inference. We did something wrong during pre-training, it will be propagated to an inference fine-tuning as well. And usually LLM doesn't have any backup options. It outputs an answer and no way to check if it's wrong. So let's talk about ensembling. It's a very famous method even in original machine learning. So basically everybody who has like minimal training in the area knows about like random forest, gradient boosting, etc., etc. In deep learning, ensemble has a little bit more background behind this. So we have this like neural network closed surface. It's usually more complicated and obviously has more than 2 weights in the whole network. But the idea is that usually the surface is very hard to predict, and we use a gradient descent to go from the point where we start to find some really good local minimum, which will help us to identify the weights that we want to use for the model. What does ensembling do? It helps us with randomization and different gradient descent modifications. It helps us to find more good local minimums, which we then can use for kind of as definitions for different models in the ensemble. What's happening if the models are far enough from each other? They usually tend to make an error on different parts of the sample, which means when we kind of ask them together for the answer, they kind of cancels out each other errors and increase the quality. So the benefits of the ensembling, it usually improves accuracy, it lowers both bias and variance. It's very simple, we train multiple models and combine the outputs, and it allows us to do it in parallel pretty easily because it's kind of independent model, and we actually can save on the training time. The main idea is that we try to use different models, and they kind of specialize in different things, and they have complementary strengths to each other, and for different various inputs, they can try to use each other's strengths and actually improve the output. Now let's talk about uncertainty again. So the ensembles has a built-in mechanism to evaluate uncertainty, since it produces a distribution of the outputs, and we can use this distribution to basically measure the confidence as how many models actually agree on the answer. And using these, we can first of all reduce uncertainty of the final model, and second of all we can try to just improve it and calibrate the model better so it has the high confidence. Let's talk a little bit about ensembling strategies. So the simplest one, we just have n models, we generate the output and use majority word or like averaging the scores depending on what we're doing, like regression classification, etc. One of the important modification on that is weighted ensemble. We basically assign each model a weight and use like the final meta learner to get their prediction. Another thing we can do is to try to sample the outputs with like specific randomness and the temperatures, so we can understand which kind of model is more important in the current setting, and use the top K averaging so we can get the better final answer. Continuing on the weighting, like standard practice with the weights for the models in the ensemble is we just assign higher weights for the model that gives better quality, which is reasonable because we want a model who makes less error to kind of has bigger load in the process. Another thing that also matters, as I explained before, like we interested in different models, so they can make errors in different parts of the sample. So for this case, the idea is to include model diversity in the weights when we optimize the final ensemble. This is part of my article, so a little bit of advertisement. You can actually read it later. But the idea is that we can calculate for the models in the ensemble how different they are from each other, and try, if we have like several similar models, we can try to give them less weight, which will mean, first of all, we will have like higher quality on the inference, and that we will be able to do it faster because we don't have a lot of the same models that we need to calculate output over and over again. Another strategy that's quite recent and LLM specific is basically prompt ensembling. It is kind of the cheap way of doing an ensemble on the language model, and we use basically the fact that it's very, very large, and if we formulate the prompt different enough, it kind of lights the different parts of the language model, which will allow us to output different reasoning paths, and then kind of again use the voting to get the final answer. This is one of the modern ways to ensemble LLMs. It's called LLM Blender. It consists of the two parts. So we have n models, and we get the output from each model. And then what do? We do the pairwise ranking. Why pairwise? Because LLM usually output text, and it's usually hard to say by how much answer A is better than answer B. We just can say, hey, this seems better, but kind of not very easy to put a number for it. Then we do like pairwise ranking for each pair of the answer, and we pick the top candidates. How do we pick top candidates? We basically just measure how frequently they output one bit all other outputs, and this is our answer. And after that, when we pick the top K, we just blend the output together. This has kind of the similar idea, but a little bit improved. So here we train the reward model, which kind of trained on the human feedback. So that when we compare two model outputs, we can actually put a number on how much one of the output is better than the other, as in probability of this model. And after that, when we try to pick the top k best basically models, answers, we can kind of not do the kind of picking the number of cases where the one answer beat the other, but use actual numbers. So this actually improves stability and reduce uncertainty for the cases where the model is not sure. Now let's talk about the effectiveness. So intuitively, like, training an ensemble is more expensive and more time consuming than training the one model, because you need train the model n times. But it's not actually true. The idea is that if we have like one big single model, it's quite a long time to train. If we have several like smaller models in the ensemble with the same number of total parameters, it actually can achieve better results as an ensemble than one single model, and it's actually faster to train because we can do it in parallel and run faster on the device and have the same accuracy. This is the plot from one of the Google papers. This is the this is the networks for the images, but we can see that it's more like Pareto effective. So basically, for the same number of resources, we can achieve higher accuracy, and it was true for the language models as well. And apart from that, there are other alternatives for training and inference, how we can speed up the ensembles. This is one of the way. So it uses it's called snapshot ensembling, and it uses the idea of why we actually do the ensembling on the neural networks in the first place. So as I already mentioned previously, we have gradient descent that goes to the local minimum of the loss function service, and this happens for the several times, and we find several local minimums. So the basic idea of the optimization is that let's say we have one gradient descent process that actually reaches several local minimums, and once we achieve each of the local minimums, we actually store the parameters, and in the end we will store these parameters, and we'll have ensemble but by the cost of training one model. This is usually speeds up the total cost for the ensemble and helps with the quality. Of course, it raises the issue with the diversity, because when we do like independent training, it's usually these local minimums not correlated to each other at all, and when we do like one process, it's usually local minimums close to each other, but we have many ways to address the diversity, and it can improve overall final quality. You can read about it in my article. Another thing is we can use parameter revision adapters. I think everybody knows about this who fine-tunes the LLMs. It's usually used to fine-tune for fine-tuning for LLM, but we can also use it as an ensemble. So basically, we have the same base for all the models in the ensemble, and then we retrain each part as just the adapter. And this is also very useful for the uncertainty estimation, because we know precisely like the part where models are different, and we can assess the diversity and how much better this specific model in the ensemble can help us with the improving quality. Another thing specific for the inference is distillation. So basically, we just train a separate model to mimic the ensemble's output and use it for the inference to speed up the process. Let's talk about actual kind of case studies where ensembles helped. Again, this is the table from my article. this is for text classification, for sentiment analysis, and for linguistic acceptability datasets. And as we can see, first of all, the ensembles obviously beat the single model in accuracy and in uncertainty estimation. And another thing, we can see that if we calculate the correlation between the model correctly and include it in the process of optimizing the weights, we can again improve the accuracy compared to even original kind of ensemble weighting, and we can improve the uncertainty as well. On the plots, the green line is basically for the ensemble with the specific measure of diversity and for quality, and we can see it goes higher than everything else, so it beats single model and every other ensembling for different problems. There are more data in the article if you're interested. Another case study is question answering for the, this is for a study from the medical question answering, which is a risk-sensitive areas where we actually want to be sure that we are giving correct answers. And we can see that LLM boosting plus voting helped achieve the plus 6% accuracy, which is usually substantial for pretty much all the tasks, and we usually are very happy with this number. And it's actually valuable to use ensembles for such important areas. Let's talk about other tasks. This is from the DeepN article, which I talked about a few slides back. We can see that usually when we use ensembling, quality is increased, and we can see that it's so simple that it can increase like quality to the 2%, even when we're talking about very small ensemble of size 2, which is kind of impressive, and in my opinion shows that we should use ensembles more in the problems where we care about quality and certainty. This is basically the simple example of why we want to use ensembling. This is a simple math problem, and LLMs famously not very good with that. If we use the single model, we can very easily get the wrong answer, but if we use ensemble and each part of the ensemble actually gives its own answer, one of the model made an error at all, but overall the errors kind of cancelled out by the other models, and the final answer is correct. Another problem which LLMs famously not very good at is kind of complicated fact checking. From what I know, the Albany is the very famous name of the city in the US, and we ask the LLM if this is actually the city with the most population. And again, one model is actually made an error, but it gets cancelled out by the other two models who are correct, which is, yeah, I already showed the quantitative values, so this is just an example of why ensembles are better and why we should use it. So for the summary, ensembles are very great with improving the quality of the model. As well as they have built-in mechanism to evaluate uncertainty and actually to optimize to reduce this uncertainty. And of course, ensembles increase the cost, and there is a trade-off between improving the quality and spending more resources. But if we know enough about efficient engineering and we use it wisely, we can actually make this cost very reasonable and improve our quality pretty cheap. Thank you.